discrete distribution, which means that they have set values. However, they are different to other discrete distributions in that they have their own unique properties and ways of finding things like the mean and the variance. But before we move on to binomial distributions, today we'll be covering Bernoulli distributions, and that's because these are a simple form of binomial distributions that we can extend into them later. So, Bernoulli distributions are defined by a Bernoulli random variable, which is a discrete random variable used when there are just two outcomes, success and failure. So a very common example that you're probably thinking of already is flipping a coin. Let's say you wanted to get a heads when you flip a coin, then it is going to be given by a Bernoulli distribution where heads is success or 1 and 0 is going to be a failure, or it's, in other words, it's going to be when you get tails. So these are actually really useful and they come up quite a bit, basically any time when you've got a success or fail event. And yeah, this is really handy. So let's look at some examples of where they are used. So turning up tail when tossing a coin, that's exactly right, because that's just the example I was using earlier. The number rolled on a die. Now, this isn't a Bernoulli distribution because it's not going to be given by a Bernoulli variable, because when we get a number rolled on a die, we've got 6 possible outcomes, so 6 possible numbers. But when we want a specific, say 6, let's say we wanted to roll a 6 on a die, then that is going to be a Bernoulli variable because it's a success if we get a 6 and it's a fail if we get anything else. But if it's just the number rolled on a die, then it means we've got 6 possible outcomes because we aren't preferencing any specific number. So hitting a bullseye when throwing a dart, that is a Bernoulli variable because when we throw a dart, we either hit the bullseye or we don't. The number of goals scored by a team in a hockey team in a match, that is not a Bernoulli variable, but a Bernoulli variable that might be related to that hockey game is whether or not you win the game or you lose the game. But the number of goals can take any number, so it's not just going to have success or fail. E. Choosing a red ball from a bag that contains red, white, and blue balls, that is a Bernoulli variable because you either get a red ball or you don't. There's no in between. So now let's look at constructing a discrete probability distribution. Well, so we want to construct a discrete probability distribution table and bar graph for rolling 6 on a die. So as I was saying, if we want specifically a 6, then that is a Bernoulli distribution because the Bernoulli variable is whether or not we get the 6 or not. It's not what is the number on the dice. So if we're going to construct a table for this, then we're going to have our random variable of x, and we've got 2 possible outcomes, 0 and 1. And then we also have our probability of getting these. So the probability that x is equal to x, and actually this should be lowercase x because this is the specific value, not the, actually, no, it should be capital X because these are the specific values. And so now constructing a table from this, what is the probability of success? Well, first of all, what is success? It's rolling 6 on a dice. So if we manage to roll a 6 on a dice, then there's only 1 out of the 6 sides that has 6, so it's going to be a 1 in 6 chance. And it fails if we don't get the 6. So that means it's going to be everything else, which means it's going to be 5 out of 6. So we either get the 6 or we don't. So now if we want to construct a bar graph from this, then we can just go with our normal bar graph. So here we have our x, capital X, because these are the possibilities for the random variables. And then we also have the probability that capital X is equal to our specific value, our lowercase x. This should all be familiar from your previous studies of discrete distributions in terms of what it should be capital and what should be lowercase x for our variables. And if you don't remember that, that's just going back to the videos that discuss that. Anyway, I'm just going to put a maximum value of 1 here because obviously the maximum possible probability we can have is 1 because that means it's absolutely going to happen. So now we have 2 possible events, our 0 and our 1. And so we just essentially fill out a bar graph. So we go up to 5 out of 6. So I'll just 5 out of 6. And then we also go up here to our 1 out of 6. And thus, we've both of these tables and then the bar graph represent the same information, just that the probability of failing or getting a 0 is 5 out of 6, while the probability of succeeding is 1 out of 6. So this is just the same information, but you'll be asked to set these up quite often. And finally, is this a uniform probability distribution? Well, no, it is not, because the probabilities of the events are not equal. If we were flipping a coin and we wanted to get heads, then the probability of success and failure would be the same, making it uniform. But in this case, because one of the probabilities is 5 out of 6 and the other is just 1 out of 6, they're not going to be equal probabilities, so they're not going to be uniform across the probability distribution. So moving on, we want to look at this as a Bernoulli distribution. So this is the general setup. We have the probability that our random variable is equal to a specific value is going to be the probability p for x is equal to 1, and then for failing, it's going to be 1 minus p. So that's exactly what we did before, where p is the probability of success. Earlier, our p was just 1 out of 6, and our fail was 1 minus 1 out of 6, which is 5 out of 6. Now, for the last example, we used our understanding of how many sides are on the dice to actually make that up. But you can do it more generally, as long as you know the probability of succeeding. If there's only 2 outcomes, then the probability of failing is just going to be 1 minus p. And that's actually a really good way to test if something is a Bernoulli distribution, as if you're given 2 possible outcomes with 2 probabilities, if this isn't true, then it's not Bernoulli. There's some other probability that you haven't considered. All right, so moving on, write a Bernoulli probability distribution for each situation. So we're going to essentially set up the same set out as before, so that same notation where we have our p, the probability that our random variable is equal to the specific value is going to be equal to, then it's going to be, we'll leave this section blank for our probabilities, but this is going to be for our success, and this is going to be for our failure. So what is the probability distribution for passing a test where probability of a pass is 56%? Well, that's actually not that bad. So we've already been given the probability of success, so we can go ahead and just write that in, 56%. So then what's the probability of failure? Well, it's going to be 100% minus 56%, which is just going to be 44%. So this is our probability distribution. It's just a very nice, easy set out where we've got the probability of success state and the probability of our failure state. So now looking at the next example, flipping heads on a coin. Well, just like I mentioned earlier, when we're doing this, the probability of getting a heads is going to be a half. So the probability of failing is also going to be half. So just writing that more formally, we have 0.5 for our random variable equaling to 1, so our success, and we have 0.5 or 50% for when we fail as well. Because they're going to be a uniform distribution, they're going to have the same values. So those are our 2 probability distributions, our Bernoulli probability distributions, because there's only 2 possible outcomes. So which of the distributions in part A are uniform probability distributions? Well, it's going to be B, or rather part 2, flipping a coin, as it's a uniform distribution because both outcomes have the same probability of occurring. So now we can look at the mean of Bernoulli distributions, which is a very important property as you've seen. So the mean, or the expected value of a Bernoulli distribution, is the expected value of our random variable equaling to p. So that's just the probability of success. That's the same p that was used when we were talking about the Bernoulli distributions. And so that's it. It's actually not that complicated. It's just, as long as you know the probability of success, that's the expected value for your mean. Well, sorry, that is your expected value or your mean. They're the same thing. So looking at some examples of that, find the mean of each Bernoulli distribution. Well, our mean is our probability of success, and we succeed whenever we have our random variable x equaling to 1. So the expected value of x in this case is just going to be when our x is equal to 1. So that's actually just going to be 4/11. And it's just that easy. And I'll just get rid of that because it looks like a minus. It's just that easy because we just have to look at the probability of succeeding. So the probability distribution here is the probability of x is equal to 9/10, 1/10 for x is equal to 1, and for x is equal to 0. So this is the same thing here, except they've simplified this. Rather than saying that your random variable is equal to x, they've just said the probability of x occurring. It means the same thing. So in this case, we're just looking again at the random variable, and we want to know when it succeeds. So when x is equal to 1, that means our probability is going to be 9/10, and our expected value is just the probability of success. So it's also just going to be 9/10. And that's it for the mean. So when you're trying to find the mean, you just look out for when the probability succeeds. So the probability of the success, and then you just take that. It's just that simple. No maths involved really there. Unless you don't know the probability of success, in which case you'd have to find it. So now looking at the variance, which again is another important property, and this tells you more so about how spread out the data is as opposed to where it is. So if we want to look at the variance or how spread out the data is, the variance is given by the probability of success times the probability of failure. And again, that's it. As long as you know the probability of success and the probability of failure, you can just multiply the two and you'll get your answer exactly how you needed it. So looking at an example, we want to find the variance of this Bernoulli distribution. So looking at the Bernoulli distribution, we've got our probability of failure and our probability of success. So this is going to be our 1 minus p, and this is going to be our p. So then we have our variance of our random variable x is equal to 1 minus p times p. So in reality, or at least rather for this example, this is going to give us variance of our random variable x is equal to 0.4 times 0.6. And you can just chuck this into your calculator and get an answer, and you're going to get 0.24. So that means your data is spread out, and if it had a higher variance or a lower variance, that would tell you more so about how to compare the Bernoulli distribution. So if one had a higher variance, then it would be more spread out than the one with lower variance. And so that's why variances can be really important. But essentially that's it with Bernoulli distributions. So what did we learn? We learned that Bernoulli distributions are distributions that have two outcomes, success or failure, and their total probability should add up to 1, which you should already know about discrete probability distributions. But we also learned how to identify Bernoulli random variables. We learned how to find the means, which is just the probability of success. And we also learned how to find the variance, which is the multiples, two probabilities multiplied, and that'll give you a variance. Anyway, I hope that this video was helpful, and I see you guys next time.